In this video, I'm going to show you how to apply the central limit theorem to the distribution of a sample proportion using the calculator. I'm going to be taking an example from page 449 in the text, in particular number 16, and I think you'd probably find it a lot easier to read along if you have the text open in front of you there. Before we launch on the example, though, let me mention a lot of students in the class are really kind of insensitive to the whole concept of propagating a round-off error. And so as they work on different problems here and there, you may take a number and instead of getting it from the memory register of the calculator, which gives you the full precision and the full accuracy, they will retype the number. And most of the time, it's really not that big of a deal because we're rounding anyway at the end, and the answer comes out close enough that you can typically tell whether you're correct or incorrect. But in this section here, we're working with a sample proportion, and it's a number which is between 0 and 1 by definition. And we're using it in calculations with lots of other numbers that are about the same size. And what you find is that for these problems, the round-off error can be very, very significant. So strongly encourage you, as you work these types of problems, make sure you don't propagate a round-off error. It's a really good way to get one wrong. Even if you understand, you can still get it wrong because you just accumulated too many round-off errors during the problem. Anyway, problem number 16 says text messaging. A nationwide study indicated that 80% of college students with cell phones send and receive text messages with their phones. A simple random sample of size n equals 200 college students with cell phones is obtained. Part A is asking, describe the sampling distribution of p hat, the sample proportion of college students with cell phones who send or receive text messages with their phones. What they're really asking with that question there is, are we able to apply the central limit theorem here? And if you look at the section, in particular page 446, you can see some bullet points there in the purple box that have to do with the sample distribution for p hat. And one of the things we want to do is verify that the normal distribution can be used as a reasonable model. And so we do that by calculating n times p times 1 minus p, and we want to see do we get something which is bigger than 10? Now in this case, n is 200. So we'll take 200 and we'll multiply that by p, which in this case is 0.8. And then we'll multiply that by 1 minus p, which would be 1 minus 0.8. Feel free to calculate that as 0.2 if you wish. And the result gives us 32, which is where we want it to be. And so that tells us that effectively that yes, the central limit theorem can be safely applied to this situation. Now, of course, if you wanted to, you could also comment what's the mean of the sampling distribution. Well, it's p. It's the population proportion, which would be 0.8. And the standard deviation can also be calculated. You can see that there in the purple box. Now, as far as part B, it's asking what's the probability that 154 or fewer college students in the sample send and receive text messages with their cell phones? Is this result unusual? Well, that's asking something that has to do with the central limit theorem. And so we can use the normal CDF to answer this question. Let's get it from the distributions menu here. Now, this says 154 or fewer. And you got to remember that's 154 out of 200. So that's your sample proportion right there. So this is a left-tailed problem, and we need some kind of a proxy for negative infinity here. Many values would work, but the one we always like to use, simply because it's easy to remember, is negative 1 times 10 to the 99, even though that's overkill here. And then the upper limit would be 154 out of 200. So we'd prefer to let the calculator do the division for us. You never know whether that is a nice decimal or a not so nice decimal. And so for that reason, it's far better to have the calculator carry the full precision there in the calculation. And then we also need to put in the mean and the standard deviation. Now the mean is population proportion, which would be 0.8. So I'll put that in. And the standard deviation is a little bit complicated. You can see the formula for sigma p hat right there on page 446 and also elsewhere in the section. Again, that's going to be a very small number, and this one in particular is very important to the distribution, so we don't want to do anything that would propagate a round-off error here, and we want to calculate it letting the calculator handle everything for us. So little bit complicated to key it in, but we'll put in a radical, and we need some parentheses. Now, my emulator software has a bug in it, and it extends the radical over the rest of the calculation. Of course, if you're doing that on your calculator, you're not going to see that, but for whatever reason, it has this bug. So it looks a little bit different on my screen here, but the calculation should still come out the same. So if you look at that, it has p times 1 minus p over n inside the radical. And so in this case, we would want to take 0.8, and 1 minus 0.8 would be 0.2. And then we want to divide that by n, which is the sample size. And that's the guts of the radical right there. So we need a closer, and then we need one more closer for the distribution. And there's your probability right there, 0.1444 and some change. Part C is asking, what is the probability that 172 or more in the sample send and receive text messages with their cell phones? It's a similar problem, but in this case it would be a right-tailed distribution, or it would be the right tail of the distribution they're asking for the area of. So probably the easiest way would be just to recycle our key sequence here, since we took the time to key in that elaborate standard deviation and everything like that. And we can just go back here and edit part of the key sequence. Now, in this case, 172 out of 200, right? So we want to take 172 divided by 200. And then our proxy for positive infinity, and it'd probably be helpful to see what we're keying here. We don't want to make some kind of mistake. So we want to key in 1 times 10 to the 99. And I have an extra 0 there. I need to delete that. So it looks like we're good to go. And there's the probability right there. Now they're asking a follow-up question. They say, is this result unusual? And again, if you recall, when they ask that question, what they're really asking is, did you get a probability which is less than 0.05? And in this case, you can see that yes, we did. And so this is most definitely an unusual happenstance. Hope that helps.